Thank you all for joining me for this area between curves video. I am Mr. Ish. When you think about area below a curve and now area between curves, there's a significant difference between the two. All along we have intuitively been looking at area below curves, especially when we're doing our integral and definite integral questions. The concept of area between curves is slightly more enhanced, and you have to know this, especially when you're going to go into the concept of volumes and curves, because if you can't calculate a region between curves, the area of that, it would be impossible for you to integrate that in terms of a volume that might come about it. Look at this right here. We have a function f over here. If you look at it from an interval a to b, we're looking here at an area below a curve. And with this function here, we're looking at everything with respect to some axis. It could have been x-axis, it could have been y-axis. Contrast this to this situation where we have a curve, let's just call that f, and we can have another curve and we'll call this g, and now you're looking again from a to b, you're looking here at an area between curves. So here there's a vast difference. Here you end up having just an integration such as this, f of x dx, from an interval a to b. In this instance you end up having a situation slightly more different. You're looking at a net effect between the two, and then you're integrating that. And why is this the case? Because when you're looking individually, we're looking here at this case, when you're looking at it individually, the f curve looks something like this, and then you're looking at all of it, all that area from a to b below the f curve. And the same situation when you're looking at the g curve, right, then you're looking at all the area below this curve within the designated interval. And then when you look at the net effect of the two, you end up looking at this area in between, which happens to be this dotted area only. So that's what you have to worry about or be concerned with when you're talking about area between curves. There are two styles of techniques and templates that you need to be aware of, and we'll be presenting those next. The number of questions that one can present for calculating area between curves with regards to integral calculus are numerous. In this video, we're just presenting the concept and the theory behind this so that when we are comfortable with this, and then in another video, we can actually look at solved examples. But we have to lay down the groundwork and the foundation so that we can understand this concept. How can we look at the two styles? One style is this. You can have a clear designation of curves such that you always have some sort of an up and down aspect to a curve, clearly from an interval a to b. If you look at both of these curves, they both seem to have some sort of an up and down orientation. When you're looking at the areas between these two type of curves, one style which pops up is this. You have something which is called a top boundary curve, yt, and you have something which is called a lower boundary curve, yb. When you're doing the integration of this area with regards to x, this style pops out. These top boundary curve, lower boundary curves are always with respect to dx, and you're always looking at them as such. You're looking at a yt minus yb. We've looked at some of this before in some of my derivation videos, but we've never looked at it formally. Here the top boundary curve is your f, here your lower boundary curve is g. But what does this y mean? The y indicates, the capital Y here indicates that you're looking at an equation which is y equals, or f of x, meaning it's a function. You're looking at it in that form, y equals equation. And everything here is with regards to dx, and your intervals are here along an x-axis dimension. That's your one style. You have a clear top boundary curve and you have a clear lower boundary curve, style number one. Style number two is of this form, where you have two types of curves, but they're more oriented in a sideways or horizontal manner, such that if this is your f curve and your g curve, and you have an interval here, now your intervals are more or less on an y-axis dimension. Here's my lower limit, here's my upper limit. And in this instance, what you end up seeing very clearly is a right boundary curve and a left boundary curve. Here's my left boundary curve, and here's my right boundary curve. When you do the area between the curve, now you're looking at things with respect to dy. You're doing everything from a lower limit boundary to an upper limit boundary. And here the form of the integral is a x or right boundary curve minus a left boundary curve dy. What does this x mean here? X means that the equations are now presented in the x equals format. And look, in both instances you still have your net effect playing through. You have a difference of 2, and that's right there is your net effect. And you see that. So here's style 1, you have top boundary, lower boundary, everything with respect to dx, equation are in the y equals format, your intervals are along the x-axis dimension. Style number 2, you have a right boundary and a left boundary curve. These type of curves are left and right oriented. You have everything here with regards to an area between those two with respect to dy, area with respect to dy, equations are in the x equals format, and you have intervals which are here in a vertically oriented manner, c and d. So you have to keep these nuances in mind. Let's look here at the concept of intervals. Generally, when you're calculating area between curves, you have intervals provided, but there are situations where an interval is not provided and you have to calculate the interval. How can you do that? It's intuitively and practically very easy to do so. If you have something which looks like this, here's an f function which kind of looks like a quadratic, and then here you have a g function which looks like a radical. You know clearly when you're looking at both of these, you're looking at in the concavities of both of these. My f function is here on the top, g function is here. When you look at the concavity of both of these, you know you end up looking at the area between the two curves, and that's the area where you're concerned with. If you're not provided the intervals, you should at least at the very minimum be provided with some sort of equation so you can determine the intervals. The procedure for determining the intervals when they are not provided is to make your equations equal to each other. Here we have f function which is really y equals x squared, the g function which is y equals root x. And you know if you were tasked with finding the area with respect to dx, you got to find horizontally oriented intervals along the x-axis. And the best way for doing that is to make the information that you're given, the equations, the functions, you make them equal to each other and you solve for x. Here you can easily take root x on the other side and you solve for x. You can isolate a root x over here. You get x to the 3 over 2 minus 1 equals 0. When you solve this individually, you get x equals 0 comma 1. And this 0 comma 1 gives you your x coordinates of an interval 0 up to this 1. And you know you can easily get the y value 0 comma 0, and this would be 1 comma 1. You just have to put these x values right here into the equation. If you put 0 into any of these equations, you get a y value of 0. If you put 1 into any of these equations, you get a y value of 1, and you've gotten your interval. That's how you can determine a good set of intervals, that is by finding intersection points of your functions. Now in the other case, if supposedly you had a function which is provided to you, you have a conic section parabola, let's just say this is y squared equals x, and then you also have an x equals 4, and you're tasked with finding the area between the curves. Here's my x equals 4, and you know the conic section parabola, a right oriented parabola is already provided. You know when you look within the concavities of these curves, this is the area you're concerned with. But you're not given the interval over here, and you're tasked with finding the area with respect to y for your interval with respect to dy. You know you got to find your upper and lower limit. How do you do that? Again, it's the same procedure. You make these equal to each other. But remember, when you're looking at everything with respect to dy, your equations have to be in the x equals format. Here's x equals y squared and x equals 4. You got to make them equal to each other. Y squared is equal to 4 and y is equal to plus and minus 2. Right? And that gives you exactly your intervals along a y-axis, minus 2 to 2. You know this right here going across would be a minus 2, this going across here would be a positive 2, and you could easily get these values here. Your x-axis value, and you wouldn't even have to do that because you already have a vertical line here. You know this right here would be 4 comma minus 2, and this right here would be 4 comma 2, and you have your intersection points. So when not provided the intervals for your questions, use the intersection determination to get to your intervals, and that's a surefire technique of doing it. We have here before us a hypothetical model made of 3 curves, and we're going to try to create an integral setup utilizing all 3 curves, but in the both means of integration we know with respect to dx and dy. Starting here with this format first, area with respect to x, we're going to look at it with regards to dx. How do we go about determining a model? Technically, if you don't have intervals provided, you have to start by finding intervals, and you do so by looking at the tug of war between the curves which are involved. When you look at this model, you have an upside down parabola which is your f curve, you have a upward parabola which is your g curve, and you have a radical which is your h curve. When you look right over here, you can clearly tell that 2 of the curves originate from the origin, so we know that with regards to area with respect to x, we can easily start something here from an interval of a 0. We can do that. When you're looking over here, you know there's a tug of war here going between the g versus the h curve right here at this intersection point. The next intersection point, as you're looking with respect to dx, you're looking along the horizontal axis, therefore your limits must go from this towards this direction. Your first intersection point is this. In this direction, you see your next intersection point is right over here. And then your third intersection point is right here. Each of these intersection points will play a key role into your interval limit. This is my first intersection, that's my second, and that's my third. When you look at your second intersection point, you see a tug of war between two functions. Here it's your h function, and here it's your f function. So h versus f, we have that tug of war between those two curves. Your last intersection point is an intersection of your g curve and your f curve. So those two curves would help you determine that intersection point. So how do we go about starting? When you're looking at this first one, this one is easy, it's 0. When we're looking at the next one right here, we could hypothetically come up with a value, and you would come up with this value by doing the intersection point here between the h and the f function. Like I showed you, you'd make both equations equal to each other and you'd solve for x and you'd get this point, and that would give you that limit. So from a limit here of a 0 up to a, what you see over here, you have a top boundary curve and you have a lower boundary curve. The top boundary curve is this radical, and it's always yt minus yb. For area with respect to x, you're always doing top minus lower boundary. So here you have a top boundary and you have a lower boundary, which is your g minus g, and that's your first part of your integral. Then you go from the next part, a, up to this run right here, because we're going from 0 to a to b. And then from a to b, at this intersection point, you would easily get the value of this b limit by doing the two equations g and f equaling to each other and solving for that x, and you'd easily do that. And here you'd see there's a top boundary curve and a lower boundary curve. From a to b, the top boundary curve is this upside down parabola, which happens to be f, and the lower boundary curve is this g curve, which is gonna come right here, and dx. So now you've already created your integral setup, and this a area with respect to x is done. You can see exactly how it's played out. Looking at the same setup, now let's try to create an integral equation or an integral form with respect to dy, calculation of the area between curves. You know, again, with all these three curves we're looking at here, this is my area between curves, all of this area right here in between. But when you're looking with respect to dy, your intervals have to be expressed in a vertical orientation along the y-axis. You know, you have to look at intersection points. When you're looking upwards, this is your first intersection point. Then as you go upwards, this happens to be your next intersection point, and then lastly that's your third intersection point. Then you draw across, and let's just draw across all the way here. My first intersection point is from origin. My next point, let's call this a C, and then let's draw this across and we call this D. So we know we're going to have two integrals. Cumulatively they must add up from 0 to D. So area with respect to y, our first integral is from 0 to C, and then we got a C. When we're looking here at 0, we have a tug of war going on here between the g and the h. So the first intersection point is easily determined, it's your origin. Your next intersection point is right over here, a tug of war between your g curve and your f curve. So g and f. You'll do the intersection of these two with regards to the y value of the coordinates, and that will help you determine your c interval. But when you're looking here from 0 to c, this interval, you can be thinking about a right boundary curve, because here you think about xr minus xl. Right boundary minus left boundary. Equations of course have to be in the x equals format, which you would have done. And when you're looking from here to here in this interval, you have a right boundary curve, which is your g function, and then you have your left boundary curve, which is your h function, and that gives you the first setup of the first part of your integral. Then you add it. These are always adding, because these cumulative effects of the integrals or the intervals adding together must always be in terms of summation. The next interval is from C to D, and we have to now determine what would be here in terms of the right and the left side boundary curve. When you're looking from here to here, you have a tug of war here, of course, between the f curve and the h curve. You could do the intersection of the two curves, and you can look at the y value, and it could give you your y limit, because these limits are here in terms of y. From here to here, you have a right boundary curve, which is your f function, and you have a left boundary curve, which is your h function, and that would be dy, and your entire integral is set up. So think about it again. From the first interval 0 to c, you have a right side boundary curve, which is this g, and you have a left side boundary curve, which is h. From c to d, you have a right side boundary curve, which is your f, and you have your left boundary curve, which is your h, and everything is exactly as I said it. We'll just close this video now with this practical work and setup over here. We're going to be doing the main examples and the practice in another video, but this is just to help us put what we've learned into effect over here. If we have these two curves, y equals sine x, y equals cosine x, and you're asked to find the area between the curves, you know you're basically looking at the area which is involved by both curves, and that would be this area right over here. And you could actually potentially look at this area right over here because it continues with that. But hypothetically, we're just looking at from this point on up to this point. You know, in this case you have a top boundary curve, and here you have a lower boundary curve. The top boundary curve is your cosine x, your lower boundary curve is your sine x. You know, this would of course be the origin. How could you calculate this interval? You do sine x, you make both equations equal to each other, and you know, if you were to carry this out, x would be equal to pi over 4. If you did this via the trigonometric function in algebra, you get pi over 4, and you know your interval would be 0 to pi over 4 along an x-axis dimension. You can do area here with respect to dx. You do from 0 to pi over 4. Your top boundary curve would be just cosine x, and your lower boundary curve would be just sine x, and you'd integrate this and it wouldn't be too hard, and you could take it into a good answer. A good thing to remember here is top boundary curve, lower boundary curve, the equations must be in the y equals format, which they are. Y equals sine x, y equals cosine x, and it won't be hard. If you were asked to find, like for an extended interval for like 0 to pi over 2, then you would continue this forward. Your interval would then go on into this part right over here, because this right here is pi over 4, and then over here you have your pi over 2, and your entire setup would expand. Your setup would expand such as this, and I'll put it out over here for example's sake. From 0 to pi over 4 you have a top boundary curve and lower boundary curve respectively cosine x and sine x. But then from pi over 4 to pi over 2, things switch, because now the top boundary curve becomes sine x and the lower boundary curve becomes cosine x. Here then it will become sine x minus cosine x, and maybe everything would zero out at the end, but this is just a setup practice, that's all what it is. But you see everything here is laid out well. In terms of area with respect to x, you have a top boundary curve in this interval and a lower boundary curve, and from this interval you have a top boundary curve and a lower boundary curve. It's always the difference of the two, and the intervals are easily determined by doing intersection points by making equations equal to each other. And lastly, for this video, let's look at this final conceptual example. We're looking here at curves which are right and left oriented. So you know you'd be thinking about here with respect to ay or dy integration. If you're tasked to find an interval for area between the curve from A to C, you know then you'd have to have two integral setups, because from A to B you have from this intersection point to this intersection point, and then from B to C you have from this intersection point to this interval, and you would have two setups which would arrive. And here you could go from A to B. From A up to B you have this as your right boundary curve, and this right here is your left boundary curve. Your right boundary curve happens to be this g function as it's written here. Your left boundary curve happens to be the f function with respect to dy, but that's just part of the interval. Then you add it for the cumulative effect. From then B to C you have now what was originally the left boundary curve has now become the right boundary curve, and that was your f function. Now the f function is your right boundary curve, and the g function has become the left boundary curve within the confines of that interval. And this is respect to dy, and this is the entire integral setup. You would have numerical values here, you would have actual equation here to actually work through, and these would generally be easy integrals to follow through, and you'd have a good numerical answer. That numerical answer would give you the area between the curves, which is represented here by the shading as you see. So keep in mind, for this specific instance, in each of these cases your equations would always be in the x equals format, as you know they should be. Here you'd have an XR, here you have an XL, right and left boundary curves, here you have your XR, and here X left boundary curve. So that's what you need to know about areas between curves. You need to know everything with respect to dx, and you need to know everything with respect to dy. This is always in the yt minus yb format, top boundary, lower boundary for that interval which is involved, and the intervals here are along the x-axis direction. With this you're looking always with right boundary curve minus left boundary curve, and here your intervals are always on a vertically oriented, and these are always values enclosed in square brackets because these are values included within the domain. And that's it for this video. In a future video on this concept of areas between curves, we'll be looking at a lot of good practical worked out questions. Thank you for watching. Have a nice day.